right, so here where we left off, we were talking about counting. We had the sum principle and then the product principle, but both of those or the sum principle was conditional on the sets being disjoint, right? But what happens when they're not? So, for example, let's say in a standard deck, how many cards are either red, or a face card? Okay, so we can again assume a standard deck. All right, so if we do that, we said, well, red, that would be half the deck, right? So 26, and face card, that is 12, and that gives me 38. But this is incorrect, all right? If we look here, all right, as we can see here, we are counting twice, right, in a few of these cards here, right? So the sum principle fails here, right? And it fails because, again, well, we are, not that it's not working, but it just does not meet the hypothesis of it being disjoint sets. So we need something else. All right, so what we have here, right, are sets that are not disjoint, right? In other words, here when we think of two sets A and B, right, we have the union, right? If this is A, B, the union of B, right, is what is all of this, right? Essentially here, here, here. All right. Now, when we talk about the intersection, right, let's say A intersection of B, here we're talking about this quantity here. All right, so that is the intersection. All right, and then one other thing that we're gonna talk about here is the idea of cardinality. So when we say the cardinality of a set, written like this, that is the number of elements. Here for our case, it'll be a discrete amount, right? A finite amount, I should say. Okay, so now in the sum principle, the hypothesis was that the A intersection of B was that if the A intersection of B was the empty set, then the cardinality of A union of B was A intersect plus B intersect. All right. Well, what do we do when they are not disjoint, right? So let's say that we had a set A and a set B. All right, so we have set A, set B. And here we have the cardinality of A intersection with B. All right, and that would be this part right here. Okay. And the cardinality of just A, right, that would be all of this right here. And then the cardinality of just B would be all this right here. However many elements that is right there. All right, so when we try to write, well, what would the cardinality of A union be? All right. Well, looking at just kind of how it's colored, this overcounts, right? I've overcounted here, right? By the intersection of A union B, right? If we look at A and B, those two, they are overlapping, right? The coloring there, right? So I double counted however much that quantity is. So to not overcount, what I need to do is I need to subtract it out, like this, right? And that is how we deal with these disjoint sets, all right? So going back to our original problem here, where we were asked, here. In a standard deck, how many cards are either red or a face card? So let's say A is red and B is a face card. So OR is the union, so A union B. So using that formula that I had, okay, so that would be how many are red. So again, we said that is 26. How many are a face card? That's 12 as before, but now let's look at the intersection. How many are red and a face card? So that would be 3, 3. So I'm subtracting off the overcount, 6, to give me the correct answer. So now this becomes 32. All right, you can see a different number, but now the correct number here. All right, so this idea here is called the principle of exclusion-inclusion, right? Where we just got to make sure that we are counting properly. Now let's take a look at what this would look like for 3 sets. Right, so let's say here we had 3 sets here. We had set A, set B, and set C. All right, so A, B, and C. All right, and again, we'll start with the intersection of all 3. A, let's get some colors working here. A, intersection B, intersection C. All right, so that would be what covers all 3 here. All right, so that looks like this, right? Okay. All right, and now let's take a look at the pairwise unions, so our intersection, excuse me, A intersection B. All right, so A intersection B would be up here. Okay. All right. And then moving along here, we have A intersection C. All right, that would be down here. And we could start to see how these piecewise are also pairwise, excuse me, not piecewise. These pairwise sets are also intersecting. And then B intersects C. All right, that would be right here. Okay. All right, and then each individual one, the magnitude of A, or the cardinality of A, excuse me, cardinality of A would be this right here. Okay, and then the cardinality of B. And so that would be this set here. And then the cardinality of C finally. That would be this right here. All right. Now, what would the union of these three sets look like, right? So now here, let's go back, A union B union C. What would the cardinality of that be? So we can start off, let's take the cardinality of A plus the cardinality of B plus the cardinality of C. All right. And as before, this is an overcount, so let's subtract those pairwise intersections. Minus A intersect B, minus A intersect C, minus B intersect C. But that goes too far here, right? Because if we note that in each one of those, right, each three of those, right, we've subtracted that middle piece there that includes all three, right? The intersection of A, B, and C. All right, so we've counted it 3 times here, and we subtracted it 3 times here, so it has gone away. So now we have to add it one more time. So we have to add in here the magnitude, the cardinality of the intersection of A, B, and C. And now we have properly counted that here. Okay, so again, and then you can imagine what this would look like if there was 4. We won't go into that one there, but you can see what the more sets we add, it gets exponentially kind of more complex here, the operation here. All right, but for this one, we see we have this this equation here, right? And what we're doing here, this is called the property of inclusion and exclusion. Okay. Right, we're including, excluding, and we have to do it in the right manner so that we make sure to count everything properly. All right, next video we'll go over a couple more examples here.